All right. Hello, hello. Today is our first video for unit number 2, polynomial and rational functions. This is one of my favorite units that we cover all year, which means it will probably be one of your least favorite units because it is very algebra heavy. All right, so those of you who still haven't mastered the skill of factoring, you're gonna want to brush up on it because we're doing it a whole bunch. All right, so let's get into it. We're going to do a quick little intro to what are polynomials and some basic things that you should remember from last year in Algebra 2. All right, here we go. Okay. So first off, we have to talk about what is a polynomial. Now, a lot of functions that we actually deal with are type of polynomials. Polynomial is like a giant category of functions. Several functions that fall into that category would be your linear functions are types of polynomials. Quadratic functions are types of polynomials. Cubic functions, those are also polynomials. All right, so really a polynomial is any function that has positive whole number exponents. Okay, so polynomial, this, like I said, is any function with positive whole number exponents. All right, and let's zoom this in a little bit. There we go. Okay, so that's a polynomial. All right, now there is, so like every function we say like has like a standard form, right? So like with linear functions, it's y equals mx plus b. With quadratics, it's ax squared plus bx plus c. Well, polynomials kind of have a standard form, but it's really ugly because, like I said, polynomials are any function that has positive whole number exponents. So its standard form looks really gross. So I'm going to show it to you guys so you can see what standard form looks like with polynomials. You don't have to write this, but just know that this is what polynomials look like. And they could have like exponents of 100. They could have exponents of just 2, right? So our standard form has to kind of cover all of those options, which is why it looks so funky. All right, so here's our standard equation. So standard form, all right, so it's a subscript n x to the power of n plus a subscript n minus 1 x to the power of n minus 1. Plus a bunch of other numbers. We're not going to write them all out, right? Well, numbers, a bunch of other terms, I guess is better to say this. All right, but then your last terms will always kind of look like this. So a sub 1 x to the first, all right, plus a sub 0 x to the 0. And this is your constant, right? This is whatever your constant is. Okay, so because, like I said, polynomials can be exponents of 100, and then, so like if we did have an exponent of 100, the first one would be, n would be 100, and the next one, it would be n minus 1, so it would be 99, and then the next one would be 98, then 97, and so on and so forth. So we're obviously not writing that, but this is kind of what your standard form looks like. All right, so a sub n, this is your leading coefficient. That just means it's the number in front of the largest exponent variable. All right, and then n, that's your largest exponent. Okay. All right, so again, you don't have to have that formula memorized, but just know that that's how standard form for polynomials looks. All right, so you start with your largest exponent in the front, and you go down by 1 exponent each time until you get to your constant term, which would have an exponent of 0, meaning it doesn't have an exponent, right? X to the power of 0 is just 1. Okay, so that's that part. So the next part is classifying polynomials. So polynomials have like two main ways to classify them. The first way you can classify a polynomial is by its degree, and that's something that we do all the time. Like I said, the fact that we have quadratic functions means that we do classify polynomials by their degree. A quadratic is a polynomial of degree 2. All right, so when you classify it by its degree, that's the classifying it by its largest exponent. All right, so this is when you classify by the largest exponent. For instance, x to the first, that's a linear function. X squared, we call those quadratics, right? All right, and then we have x cubed, so I'll write it kind of like right here, x cubed, that's called a cubic. And x to the fourth is called a quartic, but you don't need to know those. So the main three kind of polynomials that you guys have dealt with in the past is going to be your linear function, your quadratic function, your cubic function. Now we are going to deal with polynomials of higher degrees than 3. We're going to look at polynomials degree 4, degree 5, degree 6, and do different things with them. So if you have something that's in standard form, it's easy to figure out the degree. All right, so if something is in standard form, your degree is just your largest exponent, and that's usually how you guys are used to seeing them, right? So standard form, your degree is equal to the largest exponent. All right, but you guys also learned this in Algebra 2 last year. I know this was probably, this is the second unit you guys covered, so it actually was around this same time last year, so it's like October-ish, where you guys do the polynomial unit. But sometimes you're not given a polynomial in standard form, you're given that polynomial in factored form, and you have to do something a little bit different to figure out the degree of those polynomials. All right, so if it's in standard form, it's easy. It's just whatever your largest exponent is. So like I said, we have the quadratic. So if you have x squared plus 2x plus 1, we know that that is a degree of 2. It's our quadratic function, right? So when it's in standard form, it's easy. All right, so if it's in factored form, we have to do a little bit of extra work. It's not super hard, but it is a little bit different. So if something is in factored form and you wanted to find its degree, the degree is equal to the sum of the exponents. All right, so for example, I'll just kind of go off to the side here. If you were given, say, y equals 2x squared times x plus 1 times x minus 3 cubed. All right, let me scroll to, there we go. All right, so if you were given that, so this is factored form, right? So it's no longer in that big standard form, it's been factored, all right? So if you wanted to figure out the degree of this polynomial, you do have technically two options. You can multiply the whole thing out, and then whatever your biggest exponent is in your standard form, then that would be your degree. But that's a lot of work, and generally you don't want to multiply this out. That's really disgusting. So there is a trick way to kind of do this, and all you have to do is look for your exponents. All right, and you want to, basically you're just going to add them up. All right, so our first exponent is 2x squared, so there's a 2. All right, then we have x plus 1 in that parentheses. Well, it doesn't look like it has an exponent, but that parentheses happens one time. So technically, we would say it has an exponent of 1. And then our last factor, our last parentheses, x minus 3, has an exponent of 3. So if we wanted to know the degree of this example polynomial, we would say it's 2 plus 1 plus 3, which is a degree of 6. Okay, so that's how you would do it from factored form. All right, so it's a little bit strange, but it's just counting up your exponents and then adding them all together. So yeah, so that's how to find the degree if it's in standard form versus how to find the degree if it's in factored form. Okay, hopefully we got that part. You did see that last year, but I know it's one of those units that you kind of go through medium speed, right? It's also that time of year, it's like October into like close to Thanksgiving. So like sometimes you guys forget some stuff, right? But that's how you find your degree of a factored form polynomial. All right, so next we're going to talk about terms. All right, so terms are another way to classify a polynomial. And a lot of times I feel like I classify things by their terms all the time, and I'm not 1000% certain you guys know what I'm talking about when I say these words, so I want to make sure we go over this. All right, so terms are the pieces, the individual pieces of your function in standard form. Okay, so a term, these are the individual pieces of a function in standard form. All right, they're usually separated with the plus or minuses. All right, so when you have your standard form, right, you have like something plus or minus something else, plus or minus something else, plus or minus something else. Each one of those chunks is called a term, all right? And like I said, you can classify different polynomials by how many terms they have, all right? The most common ones that you guys have seen are if something has just one term, that's called a monomial, all right? So the first one, like if you just have 3x, that's all you have. This is called a monomial. Mono meaning one. The one that we deal with the most in this class is the binomial, which means you have two terms. So like 3x plus 1, that is a binomial because it has two terms. All right, and another one that you guys see, every one of your quadratics for the most part is has three terms, right? So you have the ax squared plus bx plus c, that's three terms. That's called a trinomial. All right, so this is one term, two terms, three terms. Now, obviously they have names for ones that go higher, but these are the most important names to kind of remember, right? Like I say the word binomial all the time because we square binomials a lot in this class. All right, so you'll definitely hear me say that word. So hopefully if you didn't know what a binomial was before, now you do know what a binomial is. It just means it's some kind of function that has two terms. And a term is the individual pieces. So 3x is one piece and then 1 is the other piece. Two terms, binomial. Okay, next thing we're going to talk about is multiplicity of zeros. And I kind of want to take a side note here. First off, a lot of people are confused when they see the word zero. And I understand because in math, we have a lot of words that kind of mean the same thing when it comes to zeros. All right, so if you see zeros, just know that there's like 3 or 4 different words that are talking about the same thing. So a zero is the same thing as an x-intercept. Same thing as the solution. You can also see this called a root, or factor is kind of the same, but not exactly because a factor is not just a number. So like a factor would be like x minus 1 in parentheses, that's a factor, and we can get a 0 from a factor by setting it equal to 0 and solving for x, but a factor isn't technically the same thing as a 0, right? So, but all of these words mean the same thing. So zeros, x-intercepts, solutions, roots, they're all talking about the same thing. All these words literally are talking about where your graph crosses the x-axis. Where graph crosses the x-axis. All right, so I know it's kind of confusing because there are so many words and they literally mean exactly the same thing, but that's what they mean. That's what they are. They're all the same. All four of these literally mean, where does your graph cross the x-axis? All right, so when we're talking about polynomials, we have different types of zeros depending on what we call the multiplicity. Multiplicity means how many times a zero happens, or an x-intercept happens, or a solution happens. You get the idea. All right, so multiplicity, this is how many times a certain zero happens. And again, this is something that you guys learned in Algebra 2. And even when I taught Algebra 2, I had a lot of students who either forgot this piece or maybe we didn't go over it well enough. So you have seen this before, but again, you might not remember it. And that's okay, that's why we're going over it again. All right, so multiplicity just means how many times a certain zero happens. And this comes from the exponent. All right, so we're going to look at three main types of multiplicities. All right, so sometimes a factor or a zero or an intercept or a solution or a root has a multiplicity of 1. That means your graph only contains that solution one time. All right, so if that's the case, it's going to have an exponent of 1. That tells me that that zero happens one time. Now, graphically, this is going to look like your graph is going straight through that point. All right, so this is multiplicity of 1. Graph goes straight through. Okay, like this. There's the zero. It goes straight through like a line. All right, the second type of multiplicity you guys are going to see is the multiplicity of 2, meaning that zero happens 2 times, and you're going to know that because it's going to have an exponent of 2. Think quadratic. All right, so if you have, if one of your zeros has a multiplicity of 2, it's going to look very similar to that quadratic shape. It's going to make like a U. All right, that means it's going to touch the x-axis at that point and then turn the other direction or bounce away from that point. All right, so when you graph something that has a multiplicity of 2, the graph does kind of like a bounce at that point, and that indicates that that zero happens twice. So graph bounces at the point like this. So there's your zero at the bottom. All right, it's on the x-axis, so it's going to hit it and then it's going to go away. All right, the third type of zero or multiplicity that you guys are going to see is a multiplicity of 3, and that's when your zero has an exponent of 3. All right, for this one, it doesn't do the going straight and it doesn't do the bounce. It kind of makes like a wiggle. So it looks kind of like your cubic function, all right, which makes sense, right? Because it's to the power of 3. So the cubic function kind of goes like swoosh, swoosh, like that. That's what it's going to look like if the zero has a multiplicity of 3, meaning that zero happens 3 times. All right, so the graph, it's like a wiggle, like a wiggle, wiggles through the point. So here's our point. Our graph kind of goes like this through it. So it's like, boo. All right. Now, things that are higher in multiplicity kind of follow the 2 and the 3 rule. So if it's an even number, greater than or equal to 2, it's always going to do like a bounce. If it's a larger even exponent, it's going to make the graph look really fat at that point, but it's still going to kind of bounce. It's just going to be kind of wide. Same thing with odd numbers, 3 and greater. So multiplicity of like 3, 5, 7, 9. That's still going to do the wiggle. It's just going to look kind of fatter, right? It's going to like look like it flattens out before it goes back up again. We're not going to deal with ones that have multiplicity higher than 3, but just know that that's what happens with them when they do get larger. So every even multiplicity 2 and up always bounces. It just is going to get wider the bigger the exponent is. And multiplicities that are odd, 3 and higher, are always going to wiggle. It's just going to be a fatter wiggle. Okay. Last piece we have to talk about today is end behavior. So we are going to do an example. All right, so this video is going to go kind of long. I'm going to pretty much go through end behavior rules kind of quickly because you will have graphing calculators for this, so it will be, you can always graph it and kind of see what's happening. But there are some techniques for figuring out your end behavior just by looking at a polynomial function. There's only 4 options for end behavior. All right, so option number 1, if your leading coefficient is positive, all right, so a sub n is our leading coefficient and it's a positive number. Okay, so our leading coefficient is positive and our multiplicity, or we'll say our degree, that's probably a better word, and our degree is even. All right, so this is scenario number 1. So we have a positive leading coefficient and it's an even degreed function. It will always have this type of shape. All right, and its end behavior, so the limit as x goes to infinity of this function is positive infinity, and the limit as x goes to negative infinity of this function is negative infinity. Oops, sorry, that's a lie. It's positive. All right, so if you have a positive leading coefficient and your degree is even, your endpoints will always point in the same direction and they will both always point up. Happens every time. All right, so you don't even have to put this into your graphing calculator. You'll know what your endpoints look like based on these 2 things. Positive leading coefficient and it's an even function, then your endpoints both point up every time. All right, number 2. Leading coefficient is negative. Degree is even. All right, so think of your quadratic functions. All right, so it's an even degreed polynomial, but our leading coefficient is negative. So this one, the ends still are going to point the same direction, but because it's negative, they're both going to point down. Right, and polynomials can have a bunch of humps in them. It doesn't matter, right? Quadratics only have 1, but like if you do like something to the power of 4, like a quartic, it's gonna have like a bunch of little humps, right? And when you get to the power of 6, it'd be even more humps, right? So that's just kind of what polynomials look like, right? So that's why I'm kind of drawing them like weird little humpy things, all right? But like I said, no matter what type of polynomial you have, if it has an even degree and that leading coefficient is negative, your endpoints point down on both sides. So limit as x goes to infinity of f of x is negative infinity, and the limit as x goes to negative infinity of f of x is also negative infinity. Okay, 2 left. And I'm sure you can probably guess where we're going with this one. So we did even positive, even negative. Guess what we're going to do now? Odd positive and odd negative. All right, so here we go. Number 3, a sub n is positive and our degree is odd. All right, so here's our graph. All right, and these ones are going to look something like this. All right, and if you notice our ends, they do point different directions. All right, When you're going towards the positive x's, if this is the type of function you have, your ends are always going to point up. As you go towards the negative x's, your ends will always point down. All right, so the limit as x goes to infinity of this function is positive infinity, but the limit as x goes to negative infinity of this function is negative infinity. All right, so the ends point different directions, and since it's positive, one is going up towards the positive x's, and the other one is going down towards the negative x's. All right, last but not least, we have number 4. All right, this is when a sub n is a negative number, and our degree is odd. All right, this one will look something like this. All right, and as you can see, our ends point different directions. That's a characteristic of it being an odd polynomial. All right, and when you look at it, they're going down as you move to the positive x's, and it's pointing up as you go towards the negative x's. That's because the leading coefficient is negative. All right, so the limit as x goes to infinity of f of x is negative infinity, and the limit as x goes to negative infinity of f of x is positive infinity. Oops, there we go. All right, so those are our end behavior rules. So it's kind of nice. I know it's kind of funky looking at it like this, but it's just a trick that works every time. So those of you who have a hard time figuring out end behavior, this is the way to figure them out. So you don't have to look at the graph. You don't really even have to think about it. As long as you remember these 4 rules, then you can know end behavior really quickly without having to do too much effort, just by looking at the function in standard form. Or factored form. Factored form would also work. All right. So now we're going to do one example, and then we will be done for this video. I know it was kind of long, but it was our first intro video. Those are probably going to be the longest ones because we're trying to kind of cover a lot of stuff all at one time. All right. So here is our example. It says, find the indicated values for the given polynomial and then sketch the graph. All right. This goes pretty quickly. So looking at our function, we are in factored form. All right, so this is a factored form. All right, so the first thing it wants me to find, so let me just zoom out a little bit so we can fit more on the screen there. There we go. All right, so the first thing it wants me to figure out is the degree of the polynomial. Well, since this is in factored form, I have to use that technique of adding up my exponents to get the degree of my function. So I have a 2. I don't have anything here, which means that I have an exponent of 1. And then the last one is an exponent of 3. So my degree of my function is 2 plus 1 plus 3, which is 6. So I have a 6-degreed polynomial function. All right, now if you kind of want to skip, because we just talked about end behavior, we can kind of skip down to those limits. All right, so it's an even degree. All right, so we know we're looking at one of those first 2 scenarios, right? Because those are for even degree functions, right? So now all we really have to know is our leading coefficient positive or negative? Well, this doesn't really look exactly like it has a leading coefficient, but it does. It's right here, all right? It's the thing that's out front. Right, leading coefficient, right? Coefficient's a number. So our leading number is a -2. So this would be an even function with a negative leading coefficient, which means it falls into that second category of end behavior. So I can kind of go ahead and just do my end behavior based on what I just did. So hold on, let me find my mouse. It's zooming around here somewhere. There we go. I gotta just move my head. There we go. All right, so my end behavior is I don't even need to know what the graph looks like. I already know based on the pattern, it's gonna be negative infinity, negative infinity. All right, they go the same direction because it's even, and they're both going down because of that negative leading coefficient out front. All right, so that's kind of nice. So I know that my graph is gonna be pointing down as it kind of moves off of the graph. All right, so let's get to the next part. So our x-intercepts, or the zeros of our function. All right, remember, x-intercepts, zeros, they're the same thing. All right, well, since this is in factored form for me already, we should be pretty good at figuring out how to find our x-intercepts from factored form. Remember, we just take each one of our factors and set them equal to 0 and solve for x. So we have negative 2x squared equals 0, x squared equals 0, because 0 divided by negative 2 is just 0. Square root, just 0. So we have x equals 0. Now, this does happen twice. So we can kind of go ahead and jump down to multiplicity of zeros. All right, because this has an exponent of 2, that tells me that this 0 happens 2 times, which means it has a multiplicity of 2. So x equals 0 is has a multiplicity of 2. All right, let's do our next one. So our next one is x plus 2 equal to 0. All right, that gives us x equals negative 2. That's another 0. All right, now this parentheses has an exponent of 1. So this has a multiplicity of just 1. All right, so x equals negative 2. This has multiplicity 1. All right, last but not least, that x minus 5. So we have x minus 5 equals 0. So x equals 5. All right, so x equals 5 is another one of my x-intercepts. And if you look at the parentheses for this one, it has a 3. That tells me that this 0 has a multiplicity of 3. So x equals 5 has a multiplicity of 3. Oops, a little bit off the screen there. Let's just slide you over. There we go. Okay. Last thing we have to find before we can go on to graphing this is the y-intercept. Just like when you're doing any other functions, if you want to find the y-intercept, all you have to do is plug a 0 in for x and then find your y value. All right, so that's what we're going to do. So we're going to plug a 0 in for x and find y. All right, so that is y equals negative 2 times 0 squared, 0 plus 2 to the first, and 0 minus 5 cubed. I'm going to go ahead and use a calculator because I don't want to do 5 cubed in my head. So negative 2, 0 squared, parentheses, 0 plus 2, parentheses, 0 minus 5 to the power of 3. And this, I should have known, is 0. Because we're multiplying, we have 0 out front, right? So 0 times anything is just 0. I can't believe I actually wasted my time and put that into my calculator. You guys are probably laughing at me at home. It's okay. So when x is 0, y is 0, that's my y-intercept. All right, now I'm going to head to my graph and I'm going to graph all of these pieces. So the first thing I'm going to do is plot my x-intercepts. So I have 0, negative 2, and 5. 1, 2, 3, 4, 5. All right, I have a y-intercept of 0, 0, so that's already plotted. All right, and I know what ends or what direction my ends are going to be pointing. The next thing I need to do is take into account the different multiplicities. So when x equals 0, multiplicity of 2, that means it's going to bounce at that point and it's not going to go straight through. All right, 5 having a multiplicity of 3 means it's going to wiggle through that point, and negative 2 having a multiplicity of 1 means it's going to go straight through. So this is kind of challenging to get the hang of at first, but remember, your graphs don't need to be exactly beautiful. They just need to have the right kind of direction as it goes through those intercepts. So we're going to go straight through negative 2, and we're going to come up from the bottom. Oops, that's an ugly line. All right, because that's how that end kind of starts. So we're going to go up from the bottom, go straight through. Doesn't really matter how high you go. I do not care, but we know we have to come back and we're going to do a bounce at 0 because of the multiplicity of 2. So we're going to bounce at 2. All right, and then to go through 5, we're going to do like a little wiggle. Again, I don't care how high you go. I just care that you have kind of like a wiggle through that point. All right, so we have a straight through at negative 1 or negative 2, we have a bounce at 0, and we have a wiggle through 5. That's our graph. Okay, so again, I apologize, this was a bit lengthy for a video, but it was our intro video, so we had a lot of terms to kind of talk about and go through. But hopefully that is good enough for you guys to do your homework tonight. If you do have any questions, obviously I'm available during office hours. You can come see me, or you can wait till tomorrow in class, or the next time you see me in class to kind of go over it. All right, I will see you guys in the next video. Bye.